Well, this video is about circular motion. Circular motion is a type of periodic motion, which just means that there's a repeating cycle. So it's periodic means happening over and over again. And well, we already know a little bit about oscillations, which are a type of periodic motion. And in an oscillation, of course, we define those with properties such as time period, which is the time for one complete oscillation, or frequency, or both. And so oscillations have both of those properties. The frequency of an oscillation is how many times it goes through a complete cycle per second. And as we know, that's measured in hertz. Well, this lecture, as I've said, is about circular motion. So let's see how that applies to circular motion as a periodic motion. Well, if in an oscillation the time period is the time for one complete oscillation, it's pretty obvious what the time period is going to be for circular motion. Well, it's just going to be the time for a body that's moving in a circle to complete one circle. So the time for one complete circle. So that makes sense. And just like with oscillations, it's given the symbol t, and of course it's measured in seconds is the SI unit. And the frequency of circular motion is the number of complete circles that the body goes through per second. And just like frequency for an oscillator or a wave, that's the number, it's measured in hertz. Yeah? So it's given the symbol F and it's measured in hertz. Remember that a hertz is really seconds to the -1, but it's renamed as a hertz because it's renamed as a hertz. Right, so that's just the basic idea. Let's get into it a little bit more. Well, we need to look at motion in a circle at constant speed. If something's speeding up as it moves in a circle, so in other words, the magnitude of its velocity is changing, then, well, that's pretty complex, and that's something that crops up in some options. So if you're doing that crops up later in the course. We're just looking at the moment at basic circular motion where there's a constant speed, so where a body is moving around in a circle at the same magnitude of speed or magnitude of velocity. So I might draw that a bit like this. I'm going to say that speed is v. Well, we know, don't we, that v is distance over time. And so we can kind of figure out and pretty quickly derive a useful expression, because the radius of a circle, if it's r, then we know that in one complete time period it will have gone all the way around the circumference. So we can actually say, well, that means that v in one complete time period will have gone a distance of 2 pi r. And look at that, we've immediately derived a very useful expression for what we call orbital speed. So that's the orbital speed of an object which is going at constant speed in a circle. Fantastic. Well, let's have a look at a new quantity now, because in circular motion we have to deal with something called omega. Omega, that doesn't look like omega. We know omega, don't we, as kind of the measurement of resistance. Well, that's a capital omega, and this kind of sideways W looking letter is a lowercase omega, Greek letter omega, not W. So we better call it omega. Well, omega is something called the angular velocity. Well, normal speed is distance over time. Well, angular speed or angular velocity is the angle moved through per unit time. So it's kind of really closely related in a way. And well, let's look at the circle and see what that means. Well, if I have my body again, then my blob, and it's moving in a circle this way, well, the angular velocity is not how much distance it goes through in a unit time, but simply how much angle it moves through in unit time. And the SI unit for angular velocity is the radian per second. So let's label that up. So that is called angular velocity, sometimes called angular speed, and it's sometimes called angular frequency, just to be confusing. But we'll use the name angular velocity. And the units are rad s to the -1, radians per second. But we can do a similar trick as that we did when we derived this equation over here for orbital speed. Because we can say, well, we know that in one time period, therefore, it goes through a complete cycle. So the total angle travelled through is a complete circle. Well, because it's in radians, that's 2 pi. And we've just derived another equation. Brilliant. So that's angular velocity, omega equals 2 pi over t. And we can compare, and we can see that they're actually pretty similar. The only difference really is that r there. Otherwise they're kind of the same. Well, we can actually therefore relate v and w, I've just called it w, v and omega quite well. We can say, well, yes, v equals omega times r. Yeah, v is omega, which is this bit, times r. And that gives another nice equation that links those two together. Now I really suggest learning those three, or at least understanding and being able to write them down straight away, just by thinking distance over time, 2 pi over t, or total angle over time, 2 pi over t, because they come in so useful in questions. Another couple of equations we ought to just write down to complete the picture here is the relationship between t and f. Well, t is 1 over f, and that we should recognise that from earlier on in physics, in waves and oscillations. And we can kind of combine that with the omega equation to give us a kind of alternative there, because if omega is 2 pi over t, well, 1 over t must be f. Yeah, if I flip this equation round, then I get 1 over t equals f. So that means that omega equals 2 pi f. So you might want to pause the vid and just make sure that you agree with that. And then we get these, I'm going to highlight these two as well. So we've got kind of 5 equations there, which are really, really useful. I'd learn those and have them at your fingertips. Whatever's moving in a circle, whether it's a planet, a moon, whether it's a ball on a string, a car going around a track, a washing machine drum, a roller coaster, whatever it is, all these come in really useful, and questions need you to be familiar with those. So let's have a go at a question which uses some of these so we can get a bit of a feel as to how it all works. And let's have a look. So, well, here's a question. The moon orbits the Earth in an approximately circular orbit of radius 385,000 kilometres. And the period of its orbit is 27.3 days, which is nearly a month, which we know sounds about right for the moon. Find its orbital speed, its angular velocity, and its frequency of rotation. In other words, they want us to find v, omega, and f. They've given us, what have they given us? They've given us r, and they've given us t. Well, what might be the most useful thing is let's just write down all those equations again, because then we can kind of pick out the ones we need and the ones we use. So I'm just going to write them down on the left-hand side here. So we've got v equals 2 pi r over t. We've got omega equals 2 pi over t. I love the way they're so similar. There, and we also have that is alternatively 2 pi f, because t equals 1 over f. And so that's 4 of them already. And then there's just that link between v and omega. V equals omega r. So there they all are. And I'll just hide those away in a sort of out of the way there, but we can pick and choose them as we do the question. Well, always good to have a little bit of a diagram going on. So there's the Earth and there's the Moon kind of going around and around. Well, and it's got a radius of, let's just call that r there. Well, the first question is how fast is it going round? Well, we can straight away, we can just pick that first equation there, v equals 2 pi r over t. But what we just have to be a bit careful, because if we're not careful, we'll end up with the orbital speed in kilometres per day if we just keep the numbers as they are. So let's rewrite the radius in metres first of all. Well, 385,000 kilometres sounds to me like 3.85 times 10 to the 8 metres. So there we go, we've got our radius sorted out. And let's write the orbital time period in seconds instead of days, so 27.3 days. Well, in SI units, that's going to be 27.3 times 24 times 60 times 60. And if we punch that in the calculator, what do we get? We get 2.36 times 10 to the 6 seconds. And notice I'm writing these values in 3 significant figures, because in the question, that's what they've given me, 3 significant figures. Great, so we've got R and T in nice units, metres and seconds. That's what we need. So we can now proceed. So let's do part 1. Well, part 1, V equals 2 pi R over T. So we can just plug it all in. 2 times pi times 3.85 times 10 to the 8 divided by 2.36 times 10 to the 6. And if we stick all that in, then to 3 significant figures, hopefully you agree that we get 1,030 metres per second. That's pretty fast. That's approximately a kilometre per second is how fast the moon is actually moving. That's its speed as it hurtles around in its orbit, which is incredibly fast when you stop to think about it. So let's now find the angular velocity. Well, we've got tons of choices now, because we could use v over r from here. We could use 2 pi over t from there. We could use 2 pi f. So we're spoiled for choice. And often it depends what information you've got will decide what choice you make. Anyway, we'll just go for, seeing as we've just found, we've got t in seconds, let's just do 2 pi over t. So 2 pi over t, so that's 2 pi over 2.36 times 10 to the 6 seconds, and if we chuck that in the calculator, we get 2.66 times 10 to the minus 6. Do you remember the units? Radians per second. Small number, maybe worryingly small, but it's not worryingly small, because if you think about how big a radian is from the last section, it's about, there's only 6 and a bit radians in a whole circle, and the moon's taking a month, nearly 27 days to get round there. So in 1 second it's going to go through a very, very small amount of angle. And so finally we can have a go at just getting the frequency. And again, we're spoilt for choice. We could use omega equals 2 pi f, or we could use t equals 1 over f. Looks easier, doesn't it? So let's use that one. So we know that the normal frequency, the number of rotations per second, is just 1 over t. And so if we put that in the machine, well, we get again a pretty small answer to be expected, and it's 4.23 times 10 to the minus 7 hertz. Remember, a hertz is just number of revolutions per second. And that's it, we've done the question. We've got all our values, we've written them all to 3 significant figures, and we've used a few of the equations. Well, have a go at the challenge, see if you can put those equations to use, and see if you can kind of get them at your fingertips so that you can remember them whenever you need them.